Yeah, I noticed it's pretty high. We've got some pretty good scores there too. All right. Um, Okay, so last time we talked about, we started a chapter on energy and we started talking about describing the motion of atoms and molecules. And we talked about describing it in terms of speed, velocity, acceleration. And we said that we could explain motion in terms of forces. So we said that something that's speeding up or slowing down must be experiencing an unbalanced force or a non-zero net force. Okay, and so let's just get a quick review of that with these clicker questions. We've got about four of them. So let's start with this first one. Oh, I'm sorry. That's right. I need to share it. Okay, do you see my screen now? So an object is speeding up as it moves in the negative x direction. The net force on the object is A, positive, B, negative, or C, zero. Okay, so 85% for, okay. All right. Your particle is moving in the negative x direction, so if we can take that as any direction you want. So let's just say the negative direction is going left. Okay, so if it's heading to the left and it's speeding up that way, does it mean it's being pushed or pulled to the left or to the right? So where is the direction of the force? Is it to the in the same direction? If I'm moving to the left and I'm speeding up that way, am I being pushed to the left or am I being pushed to the right? Pushed to the left. So the force must be, so your acceleration is negative, also negative, right? And your force is also negative. Okay? So you have to keep in mind that the force and the acceleration must be pointing in the same direction. If you're speeding up in the negative direction, that means you're being pushed or pulled in that same direction. So whatever the velocity is then would be the same as the force. Okay, let's try another one. Okay, here you have an atom moving in the positive x direction. So let's take our positive x direction as this one. Collides with the wall and then reverses direction. So here's your wall. Which of the following is true? The acceleration of the atom is negative. B, the force on the atom is positive. C, the force on the wall is negative. Okay. Let's see. You've got a particle moving in the positive x direction, so your velocity is positive. Okay. It reverses direction. That means your acceleration and velocity will have opposite sign. Okay, so that means the acceleration is negative. So A is correct. Okay. And so your force is also negative. So the force on the atom, if it's moving that way and eventually goes back, okay, it's moving positive originally and eventually turns around, that means something, there's a force that's pushing it in the opposite direction, in the negative direction. So the force on the atom is negative, okay? If the force on the atom is negative, then the atom must exert an equal and opposite force on the wall, so the force on the wall is positive. So the correct answer is A. Okay, looks like we need a little bit more uh, explanations on these, huh? Let's try another one, this one. When subjected to the same amount of force, which of these atoms would experience greater acceleration? A hydrogen atom or helium atom? A? Okay, good. A lighter object would experience a greater acceleration for the same amount of force. Force is mass times acceleration. So acceleration is force over mass. So for the same amount of force, if your numerator is the same, a bigger denominator would be a smaller acceleration, or a smaller denominator, smaller mass, in this case hydrogen, would have a greater acceleration. Very good. Okay. At typical atomic distances, the predominant fundamental force between charged particles is A, strong, B, weak, C, electromagnetic, or D, gravitational. In fact, this was the last thing we talked about last time. Okay, so popular answer is electromagnetic. That's correct. Okay, so uh, in other words, what we're going to be primarily concerned when we're talking about forces among atoms and molecules would be electromagnetic forces. Okay, so let's move on. So let's now actually talk about energy, because this is really our main topic. A more convenient way, usually more convenient way of talking about motions of atoms and molecules is to, instead of talking about velocities and accelerations of individual atoms, oftentimes we're more interested in the behavior of the bulk collection of atoms, and in these cases, it's more convenient to talk about energy. So let's define what we call kinetic energy. If an object, we can say kinetic energy is something that a moving object has. Okay, so a moving object is said to have a kinetic energy, and it's defined as 1/2 times the mass of the object times the square of the speed. Basically, what this says is if you're dealing with the same object, the faster it's moving, the higher the speed, the more kinetic energy it has. Okay? And if you're comparing two objects, okay, and they're both moving at the same speed, then the object that has a greater mass would have more kinetic energy. The unit for kinetic energy is called a joule, and you can see from the formula here what the unit's going to be in terms of the base SI unit. The unit for mass is kilograms, and the unit for speed is meters per second. But you have to square your speed, so meters per second, and then you have to square it. So a joule is a kilogram times a square meter times the reciprocal of the square of the seconds. Okay, so kilogram meter squared per second squared. That's your unit for energy, for kinetic energy. All right. So let's just do a quick question here. Uh, which one has greater kinetic energy? A helium atom moving at 300 meters per second, or B, a neon atom moving at 300 meters per second, or C, they have the same kinetic energy? Clicker question. B? Okay, very good. Kinetic energy is 1/2 times the mass times the square of the speed. So they have the same speed. So the one with the bigger mass would be would have more kinetic energy. What if my velocity here was negative 300 and my velocity over here was positive 300? Would that make a difference? It wouldn't make a difference. Sorry? Okay, it wouldn't make a difference because with the speed, what we're calculating here is the square of the speed, and the magnitude of the velocity is just the speed, and so since you square it, whether you have a negative or a positive number, you square it. Actually, the magnitude of the speed, velocity is the absolute value is a positive number. Okay, so the velocity, the direction doesn't matter. All right. So here's a simple example of a straightforward calculation, just to give you a ballpark figure about the typical kinetic energies of molecules. So the nitrogen molecule, let's say, 80% of the molecule in the air you breathe are N2 molecules. Okay, so the mass of a nitrogen molecule is 28 atomic mass units. You can convert that to kilograms. That's going to be 4.65 times 10 to the negative 26 kilograms. Now, at room temperature, which is around 298 Kelvin, that's 25 degrees Celsius, the average speed of nitrogen molecules is 474 meters per second. Okay, so what would be the kinetic energy of a nitrogen molecule, an average nitrogen molecule? Then you say it's going to be 1/2 times the mass, which is 4.65 times 10 to the negative 26 kilograms, times the speed, which is 474 meters per second, and then you square that. And what number do we get for that one? Let's see if I can bring up my calculator here. So I have 1/2. I'm going to square my 474 first. 474 squared, so squared, times 4.65 times 10 to the negative 26 times 1/2, so divided by 2 equals that. I'll put that in scientific notation. How do I put that in scientific notation? Okay, what is it? 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I think it's 21. So it's 5.22 times 10 to the negative 21 joules. Is that what you're getting? Okay. 5.22 times 10 to the negative 21 joules. Kilograms, meters squared per second squared, or 5.22 times 10 to the negative 21 joules. Okay, so this is a joule. So you can see in terms of joules, those are very small numbers. Okay. Okay. All right. No problem. Okay. Very good. And so again, remember your sig figs here. So three sig figs, three sig figs. The answer should also have three sig figs. The numbers 1 and 2 here in the formula, those are exact numbers. Okay. So they have an infinite number of sig figs. All right, now you'll notice the answer we got earlier, okay, was a very small number, 10 to the negative 21. For anytime you're dealing with energies of atoms and molecules in joules, they tend to be very small. So a convenient unit you need to be familiar with, it's something we use a lot, is the electron volt, okay? 1 electron volt is defined to be 1.602 times 10 to the negative 19 joules. Okay, that's actually what's going the kinetic energy that an electron gains if you were to put it between um, parallel plates that have a 1 volt electrical plates that have a 1 volt potential difference between them. Okay, so your electron's gonna this is positive. This is the positive plate. Your electron will be accelerated towards the positive plate. So if there's a 1 volt difference between them in the process of traveling from the negative to the positive end, your electron is going to gain uh, um, 1 electron volt of kinetic energy. It's going to speed up. Okay. So you heard about electrons being attracted to uh, negatives and positives being attracted, right? So let's calculate that for an electron. So you have, what did we have earlier? 5.22 times 10 to the negative 21. So let's convert that to electron volts. 5.22 times 10 to the negative 21 joules. Our conversion factor is going to be 1 electron volt over 1.602 times 10 to the negative 19 joules. So joules cancel out, and this gives us how much? So let's pull that up on my calculator. So 5.22 divided by 1.602, that gives me 3.25 times 10 to the negative third. 21 minus 19 is 10 to the negative 2. So that's about 0.0325 electron volts. Okay? Is that what you're getting? So it's 5.22 times 10 to the negative 21 divided by 1.602 times 10 to the negative 19. That gives you 0.0326. Okay, electron volts. You got it? Okay, good. All right, let's talk about work. Work is defined as the application of force over a distance. Okay, and so the formula for work is just force times the displacement delta x. Okay, so if you have an object moving, if while it's as it's moved, it moves a distance of delta x, undergoes a displacement of delta x, and a force was being applied while you were doing that, while it was moving that way, then you say you're doing work on the object, and the unit for work, okay, the amount of work is force times the displacement. Okay, the unit for work is the same as kinetic energy, it's also joule, because what's the unit for force? Force is a Newton. Okay, delta x is meters. Okay, so the unit for work is Newton times meter, and Newton is, okay, if you remember, force is mass times acceleration, and mass is kilograms, and acceleration is meters per second squared, meters per second per second. So Newton is a kilogram meter per second squared. You multiply that by meter, and you can see you end up with kilograms meter squared per second squared. So that's the same as a joule. Okay, so a Newton meter is a kilogram meter per second squared times meters, or a joule. So let's calculate the work done due to gravity when a 1 kilogram object falls a distance of half meter. Let's just assume the downward direction is positive. Okay, so we have an object here, falls a distance of half a meter. So your delta x is going to be 0.50 meters. All right, I'm just going to take the downward direction as positive. Okay, so the force of gravity is also downward. So the force is positive. What's the force due to gravity? What's it called? The weight of the object. So mass times acceleration due to gravity. Okay, and so the mass here is 1.00 kilogram. Acceleration due to gravity is 9.8 meters per second squared. So the force on this object is 9.8 joules. I'm sorry, 9.8 newtons. Okay, kilogram meters per second squared. So that's 9.8 newtons. So how much work? Oops, what did I just do? So how much work did we do on the? How much work did gravity do on this object? Force times delta x would be the work. So you say work equals force times delta x. So our force is 9.8 newtons. Our delta x is, it moved a distance of 0.50 meters. So 9.8 times 0.5, that gives you 4.9 Newton meters, Newton times meters, or 4.9 joules. Okay? So that's the amount of work that was done on the object by gravity. Okay? All right, let's talk about what's called the work energy theorem. If there is an unbalanced force on the object, the work due to that unbalanced force would just be equal to the change in the kinetic energy of your object. So work is equal to change in kinetic energy. All right. Basically what that means is this. Let's imagine an object that we talked about earlier. Okay. It moved a distance of half a meter. Okay. And we said that the work that gravity did on that was 4.9 joules, right? What that means is that this 4.9 joules, that's the amount by which the kinetic energy of the object has increased. Okay, when you drop it, it wasn't, at the moment you dropped it, its speed was 0, so its kinetic energy was 0. By the time it's traveled half a meter, its kinetic energy is now 4.9 joules. That's the same, that's another way of saying that when it went down by half a meter, it accelerated. So this is another way of keeping track of the movement of the objects. Okay, so it's gained kinetic energy, so that means it's sped up. So in fact, how can you calculate the speed now based on this? This is the same example we had earlier. A 1 kilogram object fell by half a meter. What would be the speed at this point if you started off from rest? Well, then you'd say work is 4.9 joules, so that would be the change in the kinetic energy. Okay, so that's the the final kinetic energy minus the initial. But since our initial kinetic energy is 0, we started off at rest, so the final kinetic energy, okay, so kinetic energy final at that 0.5 meter mark would be equal to 4.9 joules. How are we going to solve for the speed at that point? How is speed related to kinetic energy? Speed is 1/2 times the mass times the square of the speed. So you can equate those two and solve for the speed. Okay? So let's do a little algebra here. I'm going to multiply both sides of the equation by 2. So I have 2 times kinetic energy equals 2 times 1/2 would just be 1. So that's just going to be mass times the square of the speed. I'm solving for speed, v here, so I'm going to divide both sides by m. M cancels out. And so how do I solve for the speed, v? V is just going to be the square root of v squared, right? So it's just going to be the square root of 2 times the kinetic energy divided by the mass. So what's our speed? 2 square root of 2 times, what was our kinetic energy again? 4.9 joules divided by our mass, which was a 1 kilogram object. All right, so 1.00 kilograms. And so what's square root of 2 times 4.9? So that's going to be square root of 9.8. And let's see what happens to these units in here. Joules over kilogram, okay? Joules is a kilogram meter squared per second squared. Divide that by kilogram. Kilogram cancels out. So joules over kilogram is just meter squared per second squared. So what's square root of 9.8? Let's see, 9.8. If I want to take the square root of that, then that means I have to raise it to the power 0.5, right? So that's going to be 3.13. So 3.1 meter. And the square root of meter squared per second squared is just meters per second. So my object will now be moving at a speed of 3.1 meters per second. Right? So as it falls, by the time it's fallen half a meter, this particular object would have gained 4.9 joules, or you say it has sped up from 0 speed at the beginning to, what was that speed we have? 3.1 meters per second. Okay. Now, work can be positive or negative depending on how the force is related to the direction of motion, okay? But it's not a vector, because if your force is pointing this way, let's say, your force is moving pointing this way, but your object is moving that way, you would expect your object to slow down, right? Opposite directions, which means that it's going to lose kinetic energy. So it's going to lose kinetic energy. So delta kinetic energy, change in kinetic energy, is going to be a negative number. The final value of kinetic energy is going to be less than the initial value. So you say work here is negative. All right? Question? Okay. Now, if force and velocity, force and the displacement are pointing in the same direction, so if the force is directed this way and the velocity is directed that way, it's being pulled in the direction it's moving, then you would expect it to speed up. That means it's going to be gaining kinetic energy and work is going to be positive. Okay? So F times delta X will have the same algebraic sign. They can both be positive or they can both be negative. Positive times positive is positive, or they can both be negative. Negative times negative is also positive. So work is positive if your force and your displacement are pointing in the same direction. You would expect the object to speed up. Okay? But if your force and your displacement are pointing in opposite directions, so if your force is positive, your displacement is negative. So you're applying a force opposite to the direction of its motion, then the work is negative. You would expect it to slow down. In other words, if I was moving away from you and you were pulling me back, I'm going to be slowing down. But if I was moving away from you and you push me, that means force and displacement would be in the same direction. I will be speeding up. Okay? So positive work simply means that your object has gained kinetic energy. Negative work means your object has lost kinetic energy. So that's how you would interpret the positive and negative signs for work. All right. Now, there are several types of kinetic energy. You said kinetic energy is due to motion. The one we've been talking about is called translational energy. That's a kinetic energy because of movement, what we call movement from place to place. So translation is movement from place to place. That's called translational energy. So the energy associated with that movement is called translational energy. Now, in addition to translational energy, molecules also have kinetic energy because of the motion of the atoms relative to each other. Okay, so if you have a molecule here, okay, the movement of that entire molecule is called translation. Within the molecule, the atoms can be vibrating, okay, or the molecule itself can be rotating. So we call that relative motion of the atoms. Though that relative motion, okay, involves a kinetic energy, which we call vibrational energy and rotational energy. Now, if you just have an unbonded atom, then all that has is translational kinetic energy. It doesn't have relative kinetic energy. Let me show you a video that would illustrate that. You can find this at the Internet Archive. It's an old movie, but it's a really nice illustration of vibrational and rotational and translational motion. Okay, let me see if I can pull that up on my other computer here.
This is a reproduction of the chemical educational material study.
Let me see if we can get a good.
It may be hard to believe that the average speed of the molecules in air, which brings sound to our ears, is 1,000 miles per hour. When you see the lightning strike a mile away, it is this speed of molecular motion that brings the thunder sound some 5 seconds later.
When most people look at substances, they normally notice only the bulk properties, such as shyness, shape, or hardness. way these pack together. For example, this is crystalline mercury, and it's one. Here is ice, and it's one.
Okay, this is kind of slow. Let me speed it up to the section that I really want you to see. Hold up a second, okay?
Yeah, that's it. Oh, and it's one here. Here we are.
Okay, hold up.
Several kinds of
One. Mercury atoms are leaving the liquid and condensing at the top of the tube. Such motion like moving mercury atoms bombard. Let's look at
here.
All right,
let's look at translational motion at the molecular level.
Here in very slow motion are models of several kinds of gaseous molecules undergoing translation, that is, motion from place to place. In addition, most of the polyatomic molecules have a further kind of motion, rotation. And close examination shows still another kind of motion, vibration.
okay.
Rotation and
That didn't look really good. Let me see if I can pull up a better. Um, Let me see. B091W. Maybe I'll just show you the video right here. So it starts at around 541, 547. Okay, so here's an animation of, so this is movement. Okay, so that's movement from place to place. That's your translational motion. Okay, so this thing's rotating, and there's your vibration right there. Okay. So those are the other types of kinetic energy that a molecule can have. All right. All right. So let's do a quick check here. Which of the following does not have vibrational or rotational energy? A, a neon atom, or B, an O2 molecule? Correct. Very good. Neon atom does not have vibrational or rotational energy. So an unbonded atom by itself only has movement from place to place, so that's called translation. Okay. And a molecule which is has two or more atoms can have translation, and then within the molecule you can have vibration or rotation. Okay? All right. Now let's talk about the concept of potential energy. Any pair of hold up. Any pair of particles is said to have a potential energy due to the force that they exert on each other. So we say they have a potential energy of interaction. So the force and therefore the potential energy generally just depends on the distance between the particles. Okay, so we say then that potential energy is energy due to position because it depends on the locations of their atoms relative to each other. For any given set of particles, okay, you can take the sum of all the kinetic energies and the potential energies for all the possible pairs, and you call that your total energy for your particles. Okay, so let's look at a simple example. Let's say you just have three particles, particle 1, particle 2, and particle number 3. Okay, what would be the total energy for this set of particles? You can say the total energy is going to be kinetic energy of particle 1 plus kinetic energy of particle number 2 plus kinetic energy of particle number 3 plus potential energy due to the interaction of particle 1 and particle number 2 plus potential energy due to the interaction of particle 1 and particle 3 plus potential energy due to the interaction of particle 2 and particle number 3. Okay? Now, this sum of the kinetic energies, if your particles happen to be bound, as in a molecule, it's convenient. Instead of thinking of separate kinetic translational energies for each of the three atoms, you can think of replacing that by just the translational energy of the entire molecule and plus the rotational energy plus the vibrational energy. So when dealing with molecules, this sum of kinetic energies is usually written as translational energy plus rotational energy plus vibrational energy. If we're dealing with particles that are sort of stuck together like atoms in a molecule. Okay? All right. Now, potential energy is defined so that the total energy for any set of particles, if you were to leave them alone, okay, would be constant. And in other words, what we're saying is the total energy of the universe is constant. That's called the law of conservation of energy. So, is this something that we can prove? No, that's not something we can prove. That's an assumption we have to make and based on our observations of nature, and it's consistent with reality. So when we define potential energy, we're assuming that if something is slowing down, okay, that kinetic energy that disappeared must have gone somewhere, and so we just say, okay, we call that, wherever it went, we call that potential energy. Okay? So total energy and kinetic energy is constant. All right. So now the value of potential energy really doesn't mean anything at all. Okay. It's the change in the potential energy that's important to us. Okay. So when we write formulas for calculating potential energy, we may get the number, but that number itself doesn't really mean anything. What we're more interested in is what happens to that potential energy. Did it go up? Did it go down? Because when you have a drop in potential energy, that simply means that your kinetic energy has increased. Okay? So if my potential energy drops by 5 joules, my kinetic energy increases by 5 joules. Similarly, if you have an increase in potential energy, that simply means your kinetic energy has dropped. Okay? So whatever change in kinetic energy, in potential energy you have, the opposite change occurred in whatever change in potential energy you have, the opposite change has occurred in kinetic energy. Now, for calculations, it's customary to assign a value of 0 for the potential energy when the particles are separated at infinite distance from each other. It's not necessary, but it's convenient to do that. So when they're very far away, okay, we say that the force between them is negligible. Okay, so if the force between them is negligible, then we say that when they're moving more or less independently, so they're not affecting each other. If these two particles are not affecting each other, their kinetic energy is going to be constant, right? If they're very far away. And so your potential energy is constant. So we just say, let's just take the condition at that the potential energy at that situation to be 0. It doesn't have to be. We can assign any number to it, okay? So it's just a way for us to keep track. We're really more interested in tracking the changes in potential energy. All right. What would happen to the potential energy of an electron as it moves away from a proton? So here's a proton, and here's an electron moving away from a proton. Is this electron attracted or repelled by the proton? Attracted to the proton or repelled by the proton? Unlike charges, attract. So the force on this electron, because of the presence of a proton, is this way, right? So the force is this way, the velocity is positive, the force is negative. So in the opposite direction. So if the velocity is positive, then the force would be negative. It's in the opposite direction. So what happens to this electron as it moves away? It's being pulled back, so it's going to speed up or slow down? As it moves away, it's going to slow down. So what's going to happen to its kinetic energy as it moves away? It's going to go down. And so what's going to happen to its potential energy? It's going to go up, opposite direction, right? And what's going to happen to it once it's very far away? What's going to happen to its kinetic energy? It's going to be leveling off, right? Level off. Oops. So we say as it moves really, really far away, its kinetic energy will become constant, and its potential energy will also become constant. So if we're going to sketch potential energy versus distance, what would it look like? Okay, we usually use the letter R for distance, so we're going to plot this potential energy versus R. Okay. Potential energy as a function of R. What we'll see is, what did we say happens as it moves away? Potential energy will be rising, and it eventually levels up. It approaches a constant value. Now, when they're very far away, we're just going to assume it approaches zero. So very far away, it's going to be rising towards zero as R increases. So as distance increases, the potential energy is going to be rising, and it's going to be approaching zero as the two particles separate at to infinite separate distance away from each other. Okay, so that's what the sketch looks like for the potential energy of interaction between a proton and an electron. All right, so here's the potential energy curve for between a proton and an electron, this red curve right here, okay, this one. And let's see what happens, okay. You know that a hydrogen atom has a proton and an electron, right? So what happens, let's say that this green line right here is the total energy. So you'll notice, regardless of how far the electron and the proton are from each other, the total energy must remain the same. So let's say it so happens that this is the total energy right here, okay? What happens? At point A, let's say we have an electron separated from the proton at point A. So so at point A, so they're separated by this distance right here, okay? What happens? Let's say your electron's moving away. What did we say is going to happen to the electron as it moves away? It's being pulled back by the proton, right? So the difference here between the total energy and the potential energy, this difference right here, that's the kinetic energy. As it moves away, what happens to the difference between the potential and kinetic? Oops. So total minus potential, total minus potential, total minus potential. You'll notice as the electron moves away, okay, your potential is rising. The difference between the total and potential, you call that your kinetic energy. The kinetic energy decreases. So it slows down. Eventually, it reaches point B. What happens at point B? Your total energy is just potential. Okay, your kinetic energy at that point is zero. So the electron stops. Okay? So if the electron stops at point B, what happens to it then? At this distance right here, it stops. It's still attracted to the proton, right? So it's going to start accelerating that way towards the proton. So it's going to speed up. It reaches point A at high speed. It keeps going, it keeps going. It reaches infinite speed and crashes back into the nucleus at R, into the proton. R equals 0 is where your proton is. So according to this diagram right here, if an electron, okay, were to start at point A, move away from the proton, it's eventually going to stop at point B, turn around, crash back into the proton. Okay? So, in other words, we say you cannot have the electron go to past point B, because what happens if the electron, let's say, was at point B to begin with? Then it's just going to speed up towards the proton and crash into the proton. What happens if the electron was at point A and heading towards the proton? It's just going to keep speeding up, reach infinite speed, and crash into the proton, according to this diagram. So what we say is this region right here, we say is what we would call a classically forbidden region. Point C is a classically forbidden condition. It's not allowed. Okay, why do we say classically? Because this is a prediction based on Newton's laws. Okay, and Newton's laws is part of what we now call classical physics. And this is a prediction that in fact is incorrect based on what we now know. Because if this was correct, the atom as we know it cannot exist. Because what did we say about the atom was? You have a nucleus and you got an electron going around your nucleus. Okay? Your electron will eventually crash into the nucleus. It's not going to take very long. The atoms as we know it, the atoms that make up everything around us cannot exist if this was true. Okay? In fact, modern theory, modern physics tells us that condition C right here, point C here, is even possible. Okay? So it actually can be anywhere from very close to the nucleus to very far away, and the electron's not going to crash into the nucleus. So we're going to talk more about the modern physics that explains why you have a stable atom when we get to quantum theory. Okay, that's the modern theory that we use to explain the existence of atoms the way we picture them now, where you have electrons going around the nucleus. Okay, but this is not to say that Newton's laws are useless, because Newton's laws works well when we're using it to apply to bigger objects. Okay, and so if you use Newton's laws to predict like trajectories of rockets or airplanes or things like that, or planets, then it works just fine. But once you apply Newton's laws to the world of the very small, that's called the quantum world, the world of the electrons, then you realize that Newton's laws are really just an approximation, and it doesn't work in the world of the very small. Okay? So we'll talk more about that sometime later in the semester. But for now, let's just this is what we would call classical physics. So this is just a classical description of what's going to happen based on Newton's laws. Right? Now, shown here in red is the potential energy for a proton and an electron. Okay? Let's say the total energy happens to be this much right here. Okay? And we have got this point right here. The green line, this is at 1 times 10 to the negative 18 joules, represents the total energy. What happens when the particles are separated by 100 picometers? So your energy now is higher than the potential energy would be if they were completely separated. You remember your potential energy limit is 0, right? When they're separated at infinite distance. Well, what happens here is this. If the electron happens to be moving away, okay, what's going to happen? Its kinetic energy will be dropping. Your potential energy will be gradually rising, but it will eventually level off. So it's going to slow down some and then eventually come to a constant speed and separate from the atom, from the proton forever. Okay, and at that constant speed right there, eventually it reaches a constant speed equal to 1 times, corresponding to a kinetic energy of 1 times 10 to the negative 18 joules. But what if the electron were approaching the proton? If it happens to be approaching the proton, what's going to happen to it? It's going to speed up. Kinetic potential energy is going to be dropping. Kinetic energy is going to be increasing, increasing, increasing. It will gain a lot of speed and then crash into the nucleus. Again, that's a problem with the classical description of using classical mechanics or Newton's laws to describe the motion of electrons. Okay, but classical mechanics works pretty well when you're just describing the motion of the nuclei in the molecules, for example. So when we're talking about electrons, we see this failure of classical mechanics. But nuclei, for just bigger particles like nuclei, usually we can get a good prediction of the behavior using classical physics. Okay, so here's an example. Here's a quick question here. Which curve here represents the potential energy between two electrons? What do we know about two electrons? They repel each other, right? So we get two electrons. So let's say this electron were to move away. What force, so if that's the velocity of the electron, what force would this electron be experiencing? Attractive or repulsive? Okay, so it's going to be pushed away by the other electron, right? So what's going to be happening to the kinetic energy of this electron? Will it be speeding up or slowing down? It's being pushed. So kinetic energy will increase, right? So it's going to speed up. What happens to the potential energy? Kinetic energy increases, potential energy decreases. So this is what the potential energy is going to look like. It's going to be decreasing as the electron moves away. So this is r in distance in picometers. I have potential energy in joules here. But eventually, when they're very far apart, the potential energy is going to level off. The kinetic energy is going to level off. So this is the plot that summarizes the behavior of the two electrons. Okay, according to classical physics. Now, like I said, for electrons, most of the time that prediction is not going to work. But we're talking about something bigger like a nucleus. That is usually a pretty good description of what's going to happen. So here's an example. Let's talk about bonding within hydrogen. Hydrogen, if you recall, has a nucleus and an electron, right? So in H2, you have two atoms. So you have two nuclei there, positively charged. And they're surrounded by electrons, right? Electrons around them. So this red curve right here shows what the potential energy would be between the two nuclei, the two protons. You can see potential energy drops as they separate, okay? Because they're repelling each other. Now, what actually happens in a hydrogen molecule, in an H2 molecule, the behavior of the two nuclei is actually summarized by a potential energy curve that looks like this. So this is just two nuclei by themselves, right? Just the fact that you have electrons going around those nuclei helps those nuclei get together, and so the effective potential energy between the two nuclei would look something like this down here, the blue curve. Okay. Now this green line right here that I showed here, I'm showing here, that's the energy level that corresponds to the average value of the relative kinetic energy and the potential energy of the atoms in an H2 molecule at room temperature. So I've blown that up over here. You can see that's the average kinetic and potential energy of the two atoms in an H2 molecule at room temperature. And so what happens there? According to that diagram, let's blow that up. Let's blow it's over here, okay? So let's say that's the average kinetic energy, total energy. What happens here? What you have here are at this distance, okay? Are we about to finish? It's 8:55. You want to continue this next time? Yeah. All right, let's just finish this up next time. And oh, tomorrow we'll talk about the lab, the graphing lab, right? Okay. Thank you.